Okay, good morning, class. It's about 9:45 Wednesday morning at the Ezel residence. I'll try to make a recording. I'll try to be a little smoother speaking and speak a little faster, but I'm not promising anything. You'll notice I got my Bulldog hat for you Rebel fans. You'll just have to put up with this uh, for the rest of this meeting. Okay. The first few minutes of the meeting I have to spend setting up my screens. I've tried doing this beforehand. It didn't seem to work. So this will take me about 2 or 3 minutes. So click here and go down to this PC. Oops, wrong one. Let's do it like this. Okay, here we go. Then select my files. I'm getting there. Be patient, please. Oops, wrong one. All right, instructor resources. The first thing I want to pull up the PowerPoint for chapter 5. Okay, and then I'm going to pull up these diagrams I made. We might need them, so they'll be handy. Then let's see what else. The sketch. So I'm going to open OneNote to get the sketcher working. Test it here with this pen. Come on, start up. Okay, let me try this. Draw pen. Okay, having a little startup trouble here. Okay, now I got it going. All right. Okay, so let's go back to the PowerPoint slide if we can get there. Well, we got to share screen first. All right, you got to find that. So this is where I have trouble, I admit. All right, now if I share the screen, and we should be ready to go. Okay, most everything is up. We can pull up something else if we need it. All right, we're ready to get started. Let me enlarge this. Okay, I do want to pull up. I do want to pull up those diagrams. So see if I can find those. I don't know why they disappear. So it's operator error, I know, but all right. So I think I've got everything I need. Let's go to PowerPoint. We can enlarge it just a little bit. Let's go to slide 27. I think that's where we started. Slide 27 starts talking about again, I'll be looking at my big screen, so you'll be looking at me from the side. Sorry about that. But we've already talked about the Kelvin temperature scale and the Rankine. These are the absolute temperature scales. So to get to degrees K, we take degrees C and add 273.15. 273 is fine. To get to Rankine, we take degrees F and we add 460. So just to get me going on this, let me try this. Degrees, no, K equal degrees C plus 273. And its degrees R equal degrees F plus 460. Okay. Let's try this. Okay, so maybe I'll get better in this. All right, so we already pretty familiar with the temperature scale. Let's go to the next slide. We're talking about maximum performance, and this is a lot of text, and I don't know any other way around it but just to read it. Okay, the thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when they're operating between the same two temperature ranges, TH and TC. So another way we could say all of these, okay, we take the two temperature ranges, TH and TC, we have for a given situation, and we can calculate the maximum thermal efficiency provided by that. We'll look at the formula in a minute. So here's another way to say it. If you've got an actual cycle and it's between these same two temperature ranges and its thermal efficiency is equal to the maximum possible thermal efficiency or the Carnot efficiency, that is a reversible cycle. If you have a real cycle operating between the same two temperature limits and its efficiency is less than the Carnot or reversible efficient, that's possible. Absolutely. That's where all real world systems live. If you have a system that's operating between temperature ranges and its efficiency is greater than that predicted by the Carnot efficiency, which is the maximum efficiency, which is the reversible efficiency, then that situation is impossible. Maybe that's a better way to say it. So here are the formulas, and they're very simple. You just need to remember them, write them down, or for a power cycle, where we have we have the boiler, the turbine, the condenser, and the pump. The maximum efficiency, or you could say the Carnot efficiency, is equal to 1 minus TC over TH. Now these TCs are in absolute temperatures, either Rankine or Kelvin. For a refrigeration cycle, the best coefficient of performance you can get for a refrigeration cycle is TC over TH minus TC. Now, one thing I want to point out, when you have TH minus TC, you're looking for a temperature differential, so you don't have to have the temperatures in absolute values here. You have to have TC in absolute values. So the maximum efficiency over our coefficient of performance, or beta max, or beta Carnot, is equal to TC over TH minus TC. For our heat pump cycle, gamma max is equal to TH over TH minus TC. So there's three fairly simple equations. Now let's work a little example here. It's in the slides. Okay. And I like for you to draw this little energy flow diagram. I'll show you later how I'd like for you to draw it, not these big clumps, but with the rectangles like we saw a while ago. Like this. Let me see if I can find it. Don't have a real handy one here. Sorry. Let's go back to the slides. Well, let me just draw one. Here's what I want you to do. Let's see. Okay, let's go to shapes, triangles. I don't know. Okay, let's go to pen, shapes, triangle. Okay, I don't know why. Can't get that to work. So usually draw, they're simple. This would be the TH. This would be the TC. You have a cycle operating. I should have gave it a little more room. Cycle operating in this square here. Then you have your heat flows. And if we're talking about a refrigeration heat system, that's QH. This is QC, and you have work net input, something like that. But of course, draw it. And I'll practice these triangles. I don't know why I couldn't get the shapes to work. Maybe it's because, let me try one more time. I'm sorry I'm wasting your time. Yeah, that's what it is. You have to start with, I was using the mouse. Okay. Sorry about the jumping around. All right, let me try it with a, let's go back and pick the black pen. And let's go shapes, try a rectangle. Well, there's a nice rectangle. All right, let's see if I go shapes, rectangle again, draw another one, say down here. All right, then draw another one. I don't know if it's still set on rectangles or not. No, it's not. I have to go back and hit shapes again. Select rectangle and draw a small rectangle. Put it in the center here. And then draw a cycle, oops. And draw a cycle arrow. I'm getting there, but it's painful, isn't it? Painful for you too. All right, let's go back to the slides. Here's our example. A system undergoes a power cycle. So we know a power cycle, the cycle in here, we know the components. We don't have to draw them out. They're the boiler. So we've got a hot reservoir at 500K. That could be the flame temperature or the maximum temperature reached by the boiler. So we have QH going down into the power cycle, 100 kilojoules. We have QC being rejected into the coal reservoir, 600 kilojoules. So you can see the work out of the turbine has to be what? It has to be the difference between 1,000 minus 600. But first we need to see, let's see. All right, let's read here. Thermal and discharge in 600 kilojoules. Okay, I mentioned that. All right. Transfer to a thermal reservoir at. Okay, the different temperatures of the low temperature reservoir. 200K, 300K, and 400K. So he's giving you three little problems here, A, B, and C. For each, determine whether the cycle operates irreversibly, reversibly, or impossible. By the way, this is not hard stuff, just a lot of little things to remember. In fact, it's hard for me to make it hard. Okay, let's go here. All right, A, your high temperature, this is TC over TH. TC for A is 200 degrees. So we go through this calculation and we get 0.4. Let me go back to this slide. Okay, reservoir temperature 500, 600 kilo. Okay, so it got 100 kilojoules flowing in and 600 kilojoules coming out. And you want to see that what the, I'm not sure what he's saying here. Okay. All right, actual performance. Oh, okay. Here's the actual performance of the cycle we got here. We're given that QC was 600 kilojoules. This is 1 minus QC over QH. Sorry, I wish I could edit out that where I went around in circles there. This is the actual performance based on the actual numbers we know. 1 minus QC over QH is equal to 1 minus 600 kilojoules over 1,000 kilojoules, which is 1 minus 0.6 or 0.4. So the actual performance of this cycle is 0.4 or 40% thermal efficiency. Now, what if our cold temperature, TC, thermal reservoir temperature, was 200? Then we could calculate the maximum efficiency we could get is 0.6. And we did get 0.4. So that's possible, but it's irreversible. It's irreversible. That's not a bad thing because all real processes are irreversible. So, but it is possible and quite likely, as a matter of fact. Now, what if the cold temperature was 300 K, the cold reservoir? So 1 minus TC over TH is, by the way, 300 K is about normal temperature. That's 23 degrees C, which is what? About 70 degrees F, I think. So let's calculate the maximum or the Carnot or the reversible efficiency. All these mean the same thing. 40%, 0.4. And we've got 0.4. So that is a reversible process. It's possible, quite unlikely, but according to our criteria, it is reversible. It is possible. So let's see if we had a 400 degree. See, that doesn't give us much temperature to operate from. From 400 degrees or from 500 degrees on the hot side to 400 degrees on the cold side, not a lot of temperature. So we expect some problems. So we calculate the maximum efficiency we could have between those two reservoirs based on the Carnot efficiency criteria, and we get 0.2. And we've got 0.4. So we could say under those circumstances with that TC and that TH, that process is quite impossible. Now we're going into a little bit more about the Carnot cycle. And that's how, I'm getting the horse in front of the cart here. But the Carnot cycle was developed by a man named Carnot, of course, and he proved that this TH and this TC, this ratio, will determine what the maximum efficiency or thermal cycle you can get between those two temperature processes. So the Carnot, like I said, the Carnot cycle provides a specific example of a reversible cycle that operates between two thermal reservoirs. It's just a particular type sample. In a Carnot cycle, the system executing the cycle undergoes a series of 4 internally reversible processes, 2 adiabatic and 2 isothermal. Now there's a problem. One of your homework problems is very similar. So here's the PV diagram of this cylinder going through the Carnot cycle. Again, a Carnot cycle is like a thought process developed to help you examine cycles to see if they're possible or not. So process 1 to 2. 1 to 2 is an adiabatic compression. So Q equals 0, 1 to 2. Process 2 to 3 is an, all right, compression, we're pushing down this way. I want to see if this pen might, if I use this pen, maybe that's not quite as jerky as the cursor. I noticed the cursor was jerky, and I don't want to give anybody a migraine headache. Adiabatic compression, 1 to 2, we see you pushing down and compressing this gas. Now, an isothermal expansion would be, let's say the gas ignites or whatever, and starts expanding. Isothermal, that remains up to the high temperature. That means T equals C from 2 to 3, right along here. That's an isothermal line right there at TH. Then we go to an adiabatic expansion, and that's from 3 to 4, adiabatic expansion. Now an isothermal compression is from 4 to 1. Again, this is constant temperature along here. This is adiabatic. The vertical lines are adiabatic, and sort of the slanted lines are isothermal, meaning the temperature is the same. Okay. Now, let's apply the Carnot cycle criteria in a way to a power cycle. Now here's a power cycle. We've got our diagram like I drew for. Let me try with a pen now. That keeps the cursor and I think is easier on your eyes. Here's the hot reservoir. Here's a cold reservoir, and here's the elements in the cycle: the boiler, the turbine, the condenser, and the pump. So we have heat transfer going into the boiler. That's a flame. That's the natural gas or coal or nuclear powered heat. Get the work out of the turbine. We reject heat through the condenser to cool the fluid back down and convert it back into a liquid where we can pump it up into the boiler and start the process all over again. So you can see the process. Let's start at 1. 1 to 2 is this an adiabatic expansion through the turbine. 2 to 3 is an isothermal. It's actually an isothermal cooling. 3 to 4 is another adiabatic. You could call it compression. Really, it's not though. And 4 to 1 is the isothermal addition of heat. So Carnot proved that for this type cycle, the maximum available, the maximum possible efficiency is 1 minus TH over T7. All right, here are the Carnot corollaries. Now, it's going to seem like we just keep saying the same thing over and over. It's like we take something fairly simple and we try to make it hard. But anyway, here are the Carnot corollaries. And we've already said this in a slightly different way. The thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when each operates between the same two thermal reservoirs at TH and TC. By the way, I see I can actually draw with a pen. Interesting. All reversible power cycles operating between the same two thermal reservoirs have the same thermal efficiency. Now, he's not saying all cycles that operate through but all reversible cycles. Now, once I get this, I probably can't erase it. All reversible cycles means all Carnot cycles. And a cycle is considered reversible when there are no irreversibles. Duh. Within the system that is undergoes the cycle and heat transfers between the system and the reservoir occurs reversibly. All right, let me read that again. The cycle is considered reversible when there are no irreversibilities within the system as it undergoes the cycle and heat transfers between the system and the reservoirs. They occur reversible. Okay, all right. Now let's talk about Carnot refrigeration and heat pump cycles. If a Carnot cycle is operated in the opposite direction, the magnitudes of all energy transfers remain the same, but the energy transfers are oppositely directed. That just means if we take a power cycle and reverse the arrows of the heat transfer, it's still a Carnot cycle, just operating in the other direction. Such a cycle may be regarded as a Carnot refrigeration or Carnot heat pump cycle. So we went through the Carnot power cycle. Now we go through the Carnot refrigeration and heat pump. Now Carnot, just these cycles, adding a Carnot just means that's the fully reversible maximum efficiency you can get out of this process between the two temperature ranges operating. All right, here's for a air conditioning or refrigeration system. Beta max is the reversible Carnot efficiency, strictly dependent on the temperature of the two reservoirs. This TC over TH minus TC. Now let me see if I can get back to, all right, here's a cycle, a refrigeration cycle. We have 4 components, very similar to the number as in the power cycle. But refrigeration cycle is actually taking, heat's going the opposite direction. Up here in the condenser, the QH is going to the outside. And the QC is actually going into the evaporator. That's taking the heat from the space we want to cool. And so the heat flow is opposite. Instead of a turbine, you have a compressor. So instead of getting work out of this cycle, we have to put work in. And the maximum efficiency of this cycle is based only on the temperatures of the reservoirs, TC or TH minus C. And for a refrigeration cycle, we use TC because that's what we're interested in, cooling something. Now, when we go to a heat pump cycle, what we're interested in is heating something, getting some heat out of that cycle. So that's TH goes up here, and now instead of calling it beta, we call it gamma. And the Carnot heat pump cycle, the fully reversible efficiency, the Carnot efficiency, is now TH over the same TH minus TC. It's not hard, it's just it is several things you have to remember, I admit. So that's pretty much the end of the cycles. Let me go back and look at this if I can get back there. Oops, I think here it is. I'm learning to use these a little better. There's the air conditioning cycle. You're taking heat out of the inside of a house or a chamber or a refrigerator or whatever, and you're pumping it. Well, I shouldn't call it pump it for air conditioning. And you're transferring it outside. But now that on itself violates the second law of thermodynamics, but we have to put work in it. When you put work in it, well, that's what the second law says. You can't go transfer heat from a cold to a hot. That's going uphill without putting some work in it. So there's the refrigeration cycle, an air conditioning cycle. Let's look at the heat pump cycle. Now, again, I'm leaving the outside here and the inside here, but now what you're trying to do, what you want to do is heat the inside. So you're taking heat out from a cold area and you're transferring it to a hot area. And again, you're going against the second law. But in order to do that, you have to have this compressor. And like I explained, the heat pump and the air conditioning system are identical, except you reverse the flow of the refrigerant. In fact, you can buy commercially available heat pumps. I had one on my house in Starkville. They work very well until your outside temperature gets about around 35 degrees, and then they don't heat very well. But they are very good units. I had to use a heat pump in Starkville because we didn't have any gas. Now, most of your systems you have in your house are called split systems. They have a Freon-based refrigeration system, just like we talked about, air conditioning system, just like this. But they use gas heat. It's like a direct heat. You just heat the air and blow it out. And that's because it's less expensive if you have natural gas. It's just less expensive. It's hard to beat direct heat from natural gas efficiency. But if you don't have gas available like we did in Starkville, then a heat pump is a very good alternative. And the cycle and the heat pump unit is all in one box. And I explained how this switching valve switches the flow of refrigerant. So, and you don't ever touch it. Like in my house, if it was hot on the inside, it'd automatically switch over to the air conditioning mode and operate like this. And then if it got cool outside or cold, started to get cold, it automatically switched to the heat pump. Now, if it got below 35 or so degrees and the heat pump started to lose its ability to operate efficiently, then you always had backup resistance heating. That's just I square R heating. That's just putting a current through a resistor and getting the heat and putting it out into space. And that's when your electric bill, that's when your electric meter, that little round thing would zoom, zoom, zoom when you're in that mode. Okay, enough of that. Now, I think this is the last topic we discussed, the Clausius inequality. And we're going to study it because it's going to be the basis of entropy, which we'll study next semester, next chapter 6. And entropy will be the last thermodynamic property we'll take up. The Clausius inequality, let me try to use my pen where I won't jerk around. So the Clausius inequality is applicable to any cycle without regard for the body or the bodies from which the system is undergoing a cycle, which one receives, let me start over. The Clausius inequality is applicable to any cycle without regard for the body or bodies from which the system undergoing a cycle receives energy by heat transfer or to which the system rejects heat transfer. What that's saying, the Clausius inequality applies to a power cycle, an air conditioning cycle, or a heat pump cycle. All right. 3 slides to go, fellas. All right, so the Clausius inequality is developed from the Kelvin-Planck statement of the second law and can be expressed as the cyclical integral. That's the integral of each one of the elements in a cycle. The boiler, the compressor, let's look at power cycle. The boiler, the turbine, the condenser, and the pump. If I look at each one of those and calculate their delta heat transfer over T, I get a number. And if I add all those up numbers, that becomes negative alpha. And I know negative alpha of the cycle, it's sort of squirrely seeing that negative over there. Why didn't they put the plus alpha and say greater than or equal to 0? I don't know. I didn't develop this. I probably messed it up. All right, where the cyclic, this integral indicates integral to performed over all parts of the boundary and over the entire cycle. The B indicates the integrand is evaluated at the boundary of the system, excluding the cycle. That'd be to the environment. What all of this is going to end up saying is during a process within a cycle, say during the heat transfer to the boiler, the work output of the turbine, the heat transfer into the condenser, the work of the pump, each one of those, the entropy may increase or decrease. But when you look at the whole cycle relative to the environment, the entropy always increases. That's sort of what that means. That sort of implies that these processes are heating up the environment. And it's one way to look at it, which is true. All right. The Clausius inequality is developed from the Kelvin-Planck state. So we just said that. The nature of the cycle executed is indicated by the value of alpha of the cycle. If this alpha turns out to be equal to 0, it's the best process you can get. It's a Carnot process. No irreversibilities are present. It's a fully reversible process. If the sigma of the cycle is greater than 0, irreversibility is present within the system. That's if the cycle. So when we calculate this, we get negative the cycle. So we have to say times a -1. You just have to work with it to see. Now, if we get that the sigma of the cycle is a negative, then it's impossible. I think we need to work an example to see how I don't know. Well, okay, that's what we got. It looks goofy, but it's really not that bad. Here's a good example that'll clarify this up. A system undergoes a cycle while receiving 1,000 kilojoules of heat transfer at a temperature of 500 K. So 500 K is your thermal reservoir temperature, pushing 1,000 kilojoules of heat in. And you're discharging 600 kilojoules by heat transfer at these different temperatures. It's really the same example we worked. Using equation 513 and 514, what is the true nature of the cycle in each one of these processes? Okay, so to determine the nature of the cycle, perform the cyclic integral of 513 in each case and apply 514 to draw an equation. So here are the two heat transfers we have. Q in and Q out. Q in over TC, Q out over Q in over TH, T out over. That is the cyclical integrals of the heat transfer to the boundaries. And these temperatures represent the thermal reservoir temperatures, which are the boundaries temperature. So if we take the first one, Q in, that's transfer in, heat transfer in is positive. So we have 1,000 kilojoules over the temperature, 500. Now let's look at Q out. That's negative, so we have to put a negative sign in this case. So that's 600 over 200. So that looks like that is 2. I'm sorry, let me try this again. So let me get up in here. So that's going to be 1,000 over 500 is 2 minus 600 over 200 is 3. So that's minus 1 kilojoule per K. And that's, remember, that's equal to minus alpha. It's crazy, isn't it? So alpha itself is a minus 1 times that. So alpha is 1 kilojoule per K. And that's greater than 0. And what did our criteria say? I got to get used to that. Click. Greater than 0, irreversible or irreversibilities are present. And it's very possible. See what he said. Yeah. Irreversibility is present within the system. It's very possible, and that would be a valid for all real-world systems. Now let's do the same calculation. This time we've got the same 1,000 kilojoules of heat being pushed in from a 500 K reservoir, and we rejecting heat out of 600 kilojoules, the same as we did up here, but this time our reservoir we rejecting it out to is 300. It's just sort of like an electrical system. It's harder to push through the current if the resistance is higher. It's sort of the way it is. So 1,000 over 500 is 2. 600 over 300 is 2. So 2 minus 2 is 0. So sigma of the cycle is 0. So what does our little cheat sheet back here says? If it's 0, then it's a perfect system. It's a reversible system. No irreversibilities are present. It meets the Carnot criteria. Now the last slide, the last thing in chapter 5. Hallelujah. All right. Again, using this equation, go back to here. The cyclic integral is equal to minus alpha. And the cyclic integral, we have to look at each one of the components receiving heat or involved in heat transfer in our system. So this time we have 400 K thermal cool reservoir. We have the same 1,000 kilojoules pushed in from a 500 K source, but this time we're trying to push out our 600 kilojoules of heat to a 400 K source, and we get, so let's look at this. That's 2 minus 1.5. So that's a plus 1.5 is minus alpha. So alpha is I'm sorry, this is 2 minus 1.5. So that's a minus 0.5 for minus alpha. So alpha is equal to a plus 0.5. And that means that it's impossible. This makes sense as if this situation is the same from the reservoir pushing in the heat, 1,000 kilojoules and 500 K, it just makes sense that the process gets more difficult as the other side of the lower temperature thermal reservoir, as its in pressure or temperature increases. You just don't have as much temperature differential to pump your heat through, so it's just more difficult. So I think that's where I'll stop. And what I'm going to do this morning, I'm going to work out the HIP problems for Chapter 5 that I assign you. Again, my numbers won't be the same. And when I get them worked out, I'm going to make another video and go over those solutions. And I'm just going over to give you tips on how to work these problems. I'm not going to work them for you. So that's it. I hope you have a good day. I hope you remain safe and all your families well. Also, this is Wednesday, so Thursday morning, those of you who haven't taken test 2, I'll be sending out test 2. Then the people who haven't taken it, well, let's see who has taken it. Shion is taking it. Oh, I can't think. I think, well, anyway, embarrass myself here. I'll send it out to all of you who hadn't taken it. If you get the test anyway and you've already taken it, then I got my wires crossed. You probably ought to give me an email or text, let me know. Now, all the tests I've got so far, I have printed them out and I have them in a nice file. So if you've completed your test and email it to me, I do have it. But if I send the email out tomorrow with a test and say you need to take it again, you need to straighten me out, okay? All right, so you guys have a nice day. I'm going to stop this recording.